everyone. We are Team Deimos, the Martian rover team from the Indian Institute of Technology Mandi. Established in 2021, our team brings together students from diverse disciplines to work collaboratively in the field of space robotics and planetary exploration. This year, we are proud to present the second iteration of our rover, Maureen. Our team is divided into five specialized sub-teams. The software team handles the autonomy, navigation, and computer vision. The mechanical team designs the rover structure and drivetrain. The electrical team manages power and embedded systems. The science team develops experiments for Martian analysis. The corporate outreach team oversees sponsorships, partnerships, and public relations. The organizational structure of Team Deimos follows a vertical hierarchy, where the project lead oversees the administrative and strategic aspects of the entire project, while each sub-team is guided by their dedicated team leads who ensure efficient coordination and execution within their respective domains. As first time participants in the European Rover Challenge, we see ERC as an opportunity to challenge ourselves on an international platform, learn from some of the best robot teams in the world, and push our innovation further in the field of space robotics. For us, ERC is a chance to gain hands-on experience in solving real-world planetary exploration problems, improve our technical capabilities, and represent IIT Mandi and India on a global stage.
This year, we have migrated from an independent steering mechanism to a differential drive system, enabling us to reduce mechanical complexity and achieve an overall weight reduction of 8 kg, making the rover lighter and more power efficient. In order to activate differential drive, we had redesigned our wheels with two primary function objectives: integrated suspension capability and improved traction performance. Our C-section remains same as its core element, allowing the wheels to absorb dynamic forces from the obstacles and reduce the vibrations. The stored elastic deformation energy provides a slight reactive push in the forward direction, assisting obstacle transversal. For optimized lateral and radial traction, we have used triangular thread geometry, reducing slippage and ensuring better torque transmission across uneven terrain. From the past experience challenges in the rocker joint, where inward and outward bending occurred depending on the terrain conditions, this led to excessive stress concentration at the rocker joints and increased torque requirements during the motion. In the updated design, we ensured that both rocker beams remain parallel under all operating conditions. This significantly reduced stress on the chassis and lowers the torque demand for forward and reverse motion. We also redesigned the chassis with high modularity to improve subsystem integration and maintenance efficiency. We repositioned the robotic arm mounting to minimize chassis bending movement. Finally, we optimized the chassis width and rocker length to better suit the differential drive configuration.
This year, we have replaced I2C with CAN bus for more noise-resistant communication. We have also migrated from a single combined driver to four isolated electronic boxes, each controlling one wheel. The power distribution acts as a 24-volt hub. It uses buck converters for 5 and 12-volt rail and powers a central USB hub for communication with GPS and cameras. The power system features a plug-and-play battery secured in a custom mount with a master kill switch for a secure power cut in case of failure. We are using Jetson Nano as our main onboard compute unit.
For communications, we are using a Ubiquiti Rocket 5 AC Light pair with sector and omni antennas at the base station and Rover respectively for reliable communications for up to 900 meters at a 40 MHz adaptable bandwidth with a new secondary telemetry radio system for reliable out-of-sight communications of odometry and control signals that also acts as a fallback in extreme conditions. A new React.js based GUI for video feed monitoring, mapped environment, and GPS coordinate visualization is used to make it easy for the remote operators to operate. This year, we have reworked our entire software stack to take advantage of ROS2 and its associated frameworks. We have incorporated a mathematically fine-tuned spatiotemporal voxel layer for autonomous navigation and IMUs, GPS, and optical flow for odometry and localization. For planning, we are using A-Star Global and DWA local planners with new custom recovery behavior, which includes altering SLAM configurations with nav params. For exploratory behavior, such as finding objects or AR tags, we have employed a spiral search-based algorithm and the navigation stack for obstacle detection. For Aruko marker detection and pose estimation, we have used OpenCV. We used FastSAM for mallet, bottle, and hammer detection due to its flexibility and efficiency, along with item-specific checks such as specific colored pixels or expected sizes and proportions.
have used 4-bar mechanism for link 1 and link 2 with a novel mechanism that dynamically adjusts the mechanical advantage, give us the high torque for heavy lifting and speed when it's count. For link 3, we relocate the fifth and sixth degree of motor to the rear of link 2. This reduces the self-torque and generating a passive anti-torque effect and improving the energy efficiency. Sweeper features 4 degree of actuation with 2 independent figure and a push-pull mechanism enabling adaptive grasping of irregular objects. Additionally, we have introduced an electromagnet-based home locking system that secures the arm during the motion, reduce the vibration and increase the actuator life.
We implemented a custom back logic to avoid repeated inputs. Additionally, we use velocity set point instead of rigid position control, allowing smoother, more compliant motion for dedicated tasks like valve turning and USB insertion.
This year, the Life Sciences team has worked on a new soil collection and storage module from scratch. The Life Sciences module employs a lead screw actuated drilling mechanism designed for precise and controlled subsurface soil collection. The drilling uses a hollow core to penetrate depths beyond 20 cm, allowing efficient extraction of soil samples while maintaining structural stability. An integrated iris mechanism is used to seal the collected soil, preventing soil loss and minimizing contamination during retrieval and transfer. The vertical motion of the drill is driven by a lead screw system ensuring accurate positioning and repeatable operation. With an approximate mass of 8 kg, the mechanism is robust yet compact enough for integration within the rover, balancing strength, precision and operation reliability for field conditions. The collected soil is deposited in a storage container. We have designed a cache box which is equipped with servo motors for rapid closure and utilizes magnetic attachments to seal itself.
In our validation, the Bradford assay was conducted on a protein-free soil sample and a protein-enriched soil sample. The control remained brownish, while the enriched sample showed a clear blue shift due to Kumasi brilliant blue binding to proteins. The Ninhydrin assay produced Rohemann's purple upon reacting with primary amine groups, confirming the presence of amino acids. These results, along with prior tests, demonstrate the sensitivity and reliability of our biochemical detection platform.
We also use environmental sensors like DHT11, SCD30 CO2 humidity and temperature sensor, S12SD UV sensor to constantly monitor environmental conditions. The output of these sensors can be seen on a live web dashboard.